Welcome everyone to the Cecil Gibb Research Seminar Series of 2021, and we're now in semester 2. For those of you who are less familiar with the seminar series, this seminar series is named in honour and in memory of Professor Cecil Gibb, who was a former head of school in psychology and a foundational professor in the school, also a highly regarded university administrator as well. So just like last semester, we've got a great lineup of speakers for this semester, and I wanted to thank the seminar team who have helped to put this together. We're really looking forward to hearing from a number of different speakers over the course of the next few weeks. Let me begin by acknowledging and celebrating the first Australians on whose traditional lands we meet, and pay our respects and gratitude to the elders of the Ngunnawal people, past and present. And especially if you're joining us from campus. ANU is a place where local elders have transmitted knowledge to younger generations over thousands of years. And so it's on this site that we're very grateful to meet and share knowledge in our seminar series, and as teachers, mentors, and also students. So let me go through a few housekeeping rules and general etiquette of the seminar series before we get started. So just a reminder that the seminar has been recorded and will be available on the Psychology YouTube playlist. Upon entry to the webinar, you will have noticed that you will have been muted, and we just ask that you stay muted through the duration of the seminar. We will have question time at the end of the seminar. If you have a question, you can write them in the Q&A box below at any time, and then alternatively, you can also raise your hand, and then I will unmute you, or at least attempt to unmute you, so you can ask a question. Okay, so today we're very lucky to start our semester 2 seminar series with our own Professor Mike Smithson. Mike is a much valued member of psychology at ANU, a mentor to many, and we really thank him for setting an incredibly high standard as a member of the international academic community, the ANU community, and as a teacher in our department. Mike is the author of many highly cited books: Confidence Intervals, Statistics with Confidence, Ignorance and Uncertainty, just to name a few. Mike's also the author of over 180 referee journal articles. His primary research interests are in judgment and decision making under ignorance and uncertainty, and statistical methods for social sciences, which we'll hear more about today. So this intro won't do justice to your contributions to our department or to psychology more generally, Mike. I think that would take much more of the seminar time to do that, but I do warmly welcome you as our first speaker of semester 2. So I'll hand over to you for a moment, and then we'll go back to me in a second.
Thank you, Erin, for that very generous introduction. The seminar I'm going to be presenting is a pre-recorded video, and I recorded it for 2 reasons. One was to make sure that I actually stayed within time, and the other was to provide something that would be have a little more insurance against any vagaries of the internet. So what you'll be seeing is slides with me kind of yakking away down in the bottom corner there for about half an hour or so, but I'll be back live for Q&A.
Great, thanks, Mike. So I'll be playing it off my computer here. If there are any problems with sound or anything, just send us a quick message through the messaging function. So I'll just share my screen.
Hi, Stephen Brunel and I have been working for a little while on resurrecting a type of measurement in psychology that was abandoned a while ago, but is quite useful and therefore should be resurrected. How many of you have heard or read about Ipsative scales or Ipsative data? Numerical data are said to be Ipsative when they have to sum to a constant for individual cases. Examples include percentages that have to add up to 100, probabilities that have to add up to 1, or hours in the day that have to add up to 24. In modern terminology, this kind of data are called compositional data. Categories or bins across the data have to sum to a constant, are called the parts of composition. For example, if we divided the categories of daily activities into these 5, then we would have a 5-part composition, and the hours in the day that people would say that they spend on each of these activities would have to add up to 24. Now, early in the 20th century, Ipsative measures were employed in a wide variety of psychological testing and measurement, personality, attitudes, values, preferences, and Ipsative ratings were claimed to be more objective than the typical Likhart's rating scales. They supposedly yielded greater differentiation among ratings and diminished response biases, such as halo effects and social desirability. I'll just give one example of what was being talked about here in terms of the greater differentiation issue. A number of years ago, I had a consultancy organization that wanted to find out the extent to which employees subscribed to the organization's main goals. And so I used 2 types of scales for measuring how important people regarded those goals. One was just a rating of importance. So for each goal, they were asked to rate it from not at all important to very important. But then I also used an Ipsative approach. I said, suppose you have $1,000 to distribute across these goals to spend on achieving each of these goals. How would you divide the $1,000 up? Now, one possibility, of course, is that people could say, well, I've got 5 goals here, so I'll just assign $200 to each of them. But that's not what they did. They really differentiated among which goals they would assign more money to. Whereas for the importance ratings, everything was important. They got a huge ceiling effect on the importance ratings. So asking them to distribute $1,000 resulted in greater differentiation among the importance of the goals than asking for just importance ratings. So what happened? Where did Ipsative data go? It turned out that standard multivariate techniques just don't deal with sum constrained variables. Calculating correlation between a sum constrained variable and a non-sum constrained variable is not a valid procedure because it doesn't take the sum constraint into account. And conventional multivariate distributions, like the multivariate normal distribution for continuous data, they just don't take sum constraints into account at all. And so Ipsative data fell out of favor by the late 1980s, by the late 1970s, or early 1980s. However, it turns out that the methods for analyzing these kinds of data have all been developed in other areas like geological statistics, and it also turns out that these methods can do some very nice things that traditional methods cannot do. There are 4 good reasons for wanting to bring compositional data back into psychology. First of all, there are a lot of data that really are compositional. Second, for some kinds of measurement, compositional scales may work better than conventional rating scales. Third, some kinds of data that are not compositional can be turned into compositional data, and when analyzed can reveal insights that otherwise are not accessible. I'll give an example of this later on. And finally, the techniques for analyzing these sorts of data have been developed, and these techniques turn out to be very straightforward. Okay, so the seminar is going to take us on a tour through those methods with examples from real data sets. But first, let's take a look at what compositional data are like. Let's take the data that's summed to 1, because any other constant, we can just divide by that constant to end up summing to 1. Compositional data live in what's called a simplex. A simplex is a surface where all the points' coordinate values add up to 1. So the example I've got here is 3 dimensions, with parts A, B, and C, and all of the data have to live on this triangle, a shaded triangle. All the points on that triangle have A, B, and C adding up to 1. Okay, so here's some data from 3 patients who've been assigned to an emergency ward in a hospital, and these data are the proportions of time in the ward that each patient spent in each of 3 stages: initial registration, assessment of what their disorder is, what the problem is, their injury is, and finally treatment. Okay, well, these data have to add up to 1 because they're proportions. And here's where they are. Here's where the 3 patients are in the simplex. So what I've done is I've taken that triangle and put it face on to us. And I plotted the patient 3's data here are shown in this kind of triangular simplex with lines showing where the coordinates are. So we can see for the treatment scale, which is the green scale, its coordinate is 0.7, as it shows in the table there. For assessment, the red scale, it's 0.2, and for registration, which is the blue scale, it's 0.1. Okay, so these coordinates are kind of weird. They're not rectilinear coordinates like Euclidean space, but you can still kind of understand how these data sit in the simplex. Unfortunately, when we get beyond 3 dimensions, the simplex starts to become really not intuitive. So we need ways of moving out of it while preserving the structure of the data so that we can understand the data better and analyze it. The most popular method for doing this is to use ratios of the parts and transform those ratios into Euclidean space by taking logarithms of them. Okay, that sounds a little bit complicated, but I'll explain in detail shortly. And all of this was worked out in the 1980s by people mainly in geological statistics, particularly by a British statistician named John Aitchison. This goes to show that what is a problem in our discipline may have been solved in another. Psychologists should look outside of their discipline more often than I think that they generally do. Okay, so let's consider some real data and look at how to get out of the simplex by dealing with these log ratio things. I've got here data from 4 patients, each of whom was assessed at a different level of severity, which is what the triage level refers to. Triage level 1 or 2 is the most serious, usually life-threatening, and then triage 3 is less serious, triage 4 is less serious again, and so on. Okay, so I've got 4 patients, each one in each triage level, and the proportions represent the proportions of time they had to spend in each of these three stages. Now, suppose we're interested in increasing the relative amount of time the patients spend actually getting treated, in other words, in Y3, the physician disposition stage. We want them to spend more time there than they do relatively in the other 2 stages. In that case, we would be interested in the ratio of the proportion of time they spend in registration to the proportion of time spent in the physician stage, and also the proportion of time spent in assessment relative to the physician stage, those 2 ratios. Okay, so we can see that the proportions of time spent in those first 2 stages increase as we go up in the triage level. And you can see this also, the decreasing in terms of the amount of time, relative amount of time spent in the physician stage. But how can we test this in a regression model? Well, first, we would take what are called additive log ratios. We take the ratio of the first 2 parts of the composition to the third, what's called the referent part. So we're taking, as I said before, the ratio of the time spent in registration relative to the time spent in the physician stage, and the time spent in the assessment stage relative to the time spent in the physician stage. And then we take the log of those ratios. What happens when you take the log of the ratio of a couple of probabilities is you end up with a variable that is on the real line. So these variables they're not sum constrained. They don't have to add up to anything. And they can take negative and positive values. They happen to all take negative values here, but they can take negative and positive values, and the values can go from negative infinity to positive infinity. We can analyze these with plain old linear regression. That's it. That's how to get out of the simplex and get these data to the place where we can actually start analyzing them with conventional techniques. So we can see that the differences between the log ratios quantify the changes in the amounts of time spent in each of the first 2 stages relative to the third as we move up in triage levels. All these differences are positive because as we move from one triage stage to the next, more time is being spent in each of these stages relative to the third stage. Okay, well, additive log ratios do have a major limitation, and that is that they require that we choose one of the parts of the composition as the referent part. And sometimes that choice can be arbitrary. In the example I've been giving, it's not arbitrary. It does make sense to choose that third stage as the reference stage. But there are lots of situations where no such choice would really come to mind. Fortunately, this is not the only kind of log ratio we can take. There are many others. I'll just give one other example. One alternative is what's called the centered log ratio. That uses the ratio of each of the composition parts, each of the YKs, relative to their geometric mean. So this horrible looking formula here just takes YK and divides it by the geometric mean of all the Ys. This pi term here is the product from j equals 1 to k of all the y sub j's, and then we take the root of that, 1 over k, to get the geometric mean. The additive log ratios, what we're looking at before, are analogous to base group coding categorical variables in linear regression, whereas centered log ratios are analogous to effects coding categorical variables in linear regression. Which one should we use? Well, it depends really on the goals that you have for your analyses, what you want to find out, and what hypotheses you want to test. Okay, so now let's put all this to work in an application. The data are from are real data from recorded information on patients admitted to an emergency department in a University of Alberta hospital. The authors of the paper that I got, from which I got the data, were interested in predicting the length of stay in the emergency department. They wanted to find predictors that would shorten the length of time that people have to spend in the hospital. And they found that patients in the intermediate triage levels had the longest lengths of stay, and also that the use of diagnostic or specialist interventions were associated with longer lengths of stay. Those were their main findings. But what about the proportions of stay that are spent in the early stages, the bureaucratic ones, registration, assessment, prior to actually getting treated? Ideally, we would want as much of the time that people spend in the hospital to be in being treated. So what predicts larger or smaller proportions of time being spent in the earlier stages? In other words, what would we find out if we made these data compositional? So that's what I've done. Denote the proportions of stay denoted in the registration, nursing assessment, and physician treatment stages by YR, YN, and YP, respectively. And what we want to do is to have two linear regression models, one of them predicting the log of the ratio of YR to YP, the other one predicting log of the ratio of YN to YP. I'm going to call these lambdas. The log ratios are lambdas. Better still, we can have one regression model with a dummy variable that distinguishes between YR and YP, or YR and YN rather. So in this model, the dummy variable B equals 1 when it's YN, when it's the nursing assessment stage, and it's 0 when it's registration. Okay, so what happens when we actually do the analyses? Well, first of all, our model accounts for a good, healthy 46% of variance in the lambdas, the log ratios. The results show that the more severe triage levels, levels 1 to 2 and 3, those predict smaller proportions of time in the first two stages. Now, this is quite different from the finding that the original authors had, where they were looking at length of stay and finding that it was triage levels 3 and 4 that predicted longer lengths of stay. Because here we're addressing a different question. Length of stay actually does have a predictive effect. The longer the length of stay, the less time is being spent in those first two stages. And finally, whether the person arrived by ambulance or whether they were a walk-in, and also the whether specialist interventions were used, have negative effects. But these are moderated by assessment and by registration. So the effects are not as big for the assessment stage as they are for the registration stage. Okay, so is any of this useful? Well, first of all, we've just seen a completely different perspective on the same data from the viewpoint that the authors had, which has provided very different answers to a different set of questions from the ones that the authors are able to address. And in fact, I went back and contacted the lead author of that paper, explained what we did, and he responded by saying he wished he'd known about this. Let's recall that they found that patients in the intermediate triage levels have the longest length of stay and the use of diagnostic imaging, especially consultation, were associated with longer lengths of stay. We've identified a need to focus on the more serious triage levels. And in fact, Dr. Yun, when we were discussing our findings with him, observed that many of our findings probably could be accounted for by the seriousness of the patient's condition. Those in the lower triage levels were arriving by ambulance, often are critically ill or injured with life-threatening injuries. Their diagnoses are clear from the start, so the early assessment stages can be all but skipped in order to get them into treatment quickly. And secondly, those in the higher triage levels 4 and 5, are not only less urgent, but they may be more difficult to diagnose, so it takes more time for the initial assessment stages. Okay, so far, so good, but all of this has an important Achilles heel. Log ratios are not defined when there's a 0 in there. So what if a patient spent no time in the nursing assessment stage, for example, and there were zeros in these data? How can we analyze compositional data that has 0s or 1s? This is a bad problem. And in fact, the geological statistics people have wrestled with it for some time. They don't have a complete answer for it. There are 4 ways we can deal with 0s and 1s in compositional data. First of all, it may be possible to just get rid of them, because they're actually due to the rarity or the sparseness of the data in one or more of the compositional parts. So we just collapse those parts with parts that are related to them. That's the same kind of thing where we collapse categories on a nominal variable, for example, when one of them has sparse data. If there aren't very many 0s or 1s, and they're not of any distinct interest to us, then we can transform them away from 0, 1 by an appropriate shrinkage transform, as is tradition widely practiced in other techniques for dealing with proportions. However, that doesn't preserve the original probability ratios. So in shrinking things, we're actually altering the data structure a little bit as well. There's a way we can do this kind of thing without altering the non-zero data structure, and that's just by replacing the 0s with some small positive value, which I'm calling epsilon, and then multiplying the non-zero values by 1 minus j times epsilon, where j is the number of 0s that we're replacing. That preserves the probability ratio. A fourth approach, which is not mentioned in the geological stats literature, which I came up with, is just something that's called a hurdle model. A hurdle model treats the 0s and 1s as if they're qualitatively distinct from the non-zero values in the 0 and interval. So the 0s are represented by a binary variable, and the 1s are represented by a binary variable as well. And then these binary variables are modeled by separate logistic regressions. And then the non-zero, non-1s values are modeled by log ratios, which is what we just did before. Okay, well, there's an additional limitation in the conventional compositional data literature. Namely, these people don't analyze variance. They just analyze the means, just like psychologists do. Analysis of variance doesn't analyze variance. Neither does traditional linear regression. They assume that variance is constant across conditions, or they assume homoscedasticity. That's not analysis, it's an assumption. But variance is really important for modeling bounded variables. If you've got bounds, then as the mean approaches any of these bounds, the variance has to shrink. It has to shrink. It's not like the normal distribution where you can pull the mean up and down without changing the variance. So this is a real problem. We need to model variance when we're dealing with compositional data. The trick is to include predictors of dispersion as well as location in linear regression. So to have 2 submodels, one predicts where the mean is going to go and the other predicts where the variance is going to go. And actually good statistical packages exist for doing this and have been around for a long time. So what I've done in our examples, I've just done this in R using the Gambles package, which allows us to do heteroscedastic linear regression. So here's the dispersion submodel from that regression. I've just shown you before what the location model submodel was. Here's the dispersion model. It turns out that triage level 3 has a less variance than the other levels, triage levels, and procedural interventions also reduce variance as well. These effects probably indicate that procedures in these situations are more standardized than procedures in other conditions, and therefore take uniform amounts of time. The amounts of time don't vary very much for them. There's another limitation on compositional data analysis, as conventionally done in geostats. If we think about analyzing a continuous doubly bounded variable, say a variable that sits between 0 and 1, we typically would use a beta distribution for that. Jay Verkon and I introduced beta regression into psychology back in 2006. But all the compositional data people used normal distributions, normal linear regression for compositional data. Why can't we use beta distributions there as well? Well, it's because they're log ratios, and you can't use beta distributions to model log ratios because those sit on the real line. They don't have any bounds. So we could use the beta distribution, see if only the data were probabilities instead of log ratios. So I converted the log ratios into probabilities. Suppose we get a log ratio or lambda jk, which is the log of yj divided by yk. To convert it into a probability ratio, we just take yj and divide it by yj plus yk. Done. For every log ratio, there's an equivalent probability ratio. Therefore, for every regression model that predicts a log ratio, there's an equivalent regression model predicting the probability ratio. And so the normal linear regression model for log ratios is identical to a logit normal regression model for probability ratios. Okay, so now we can use beta distributions, beta and other distributions. So we can model probability ratios with any distribution for variables that sit between 0 and 1. We can use beta distributions. We can use other distributions like the CDF quantile family that I invented. And so probability ratios can be everything log ratios can do and more. In fact, we combine these alternative distributions with some multivariate techniques, such as something called populus. Then we really expand the toolbox for compositional data. So let's see how this works in another example. What I'm going to do in this example is I'll compare the linear normal regression model with a beta regression model. Our example this time consists of employment data and GDP, gross domestic product per capita, in 188 countries, measured in 2015. And the employment figures are proportions of employed people who are female versus those who are male, and from each of 3 sectors: agricultural, industrial, and services. So we've got 6 parts: males and females in agriculture, males and females in industry, and females and males in service. These 6 parts form composition because for each country, they have to have 1. Now let's suppose we want to test 2 hypotheses about the effects of GDP per capita on relative employment rates. Hypothesis 1 is that in wealthier countries, female employment rates relative to male employment rates will be higher in the service sector and lower in the other 2 sectors. And 2, in wealthier countries, the employment rates for both men and women combined in both agricultural and industry will be lower relative to employment rates in the service sector. Okay, so how are we going to test this? We can test this by setting up the following probability ratios. These first 3 compare the females in each of the 3 sectors: agriculture, industry, and service, with their male counterparts. So these test hypothesis 1. The last 2 combine male and female rates in agriculture and male and female rates in industry, and compare them against male plus female rates in services. Okay, so what happens when we subject these to a budget normal model and also to a beta regression model? They mostly agree on their location submodels and therefore on the tests of hypothesis 1 and 2. So let's take a look at this. Hypothesis 1 is supported by both models. So in both your countries, female regression rates in both industry and agriculture are lower as wealth goes up. In the service sector, they become higher. So all these effects are significant, all in the right direction. Hypothesis 2 also is supported by both models. The coefficients are quite similar to each other again. The employment rates are lower in agriculture and industry relative to service sector as wealth goes up. Here's a typical example of a location submodel plot for agricultural services. These are fitted values for the logit normal, which are the open circles, and the beta model, which are the closed circles. You can see that the two models are doing effectively the same thing. But when we come to the dispersion submodels, we find that now we've got two models that don't always agree with each other. Okay, so for the females versus males in industry, the logit normal model says there isn't any effect of GDP per capita, whereas the beta model says there is an effect. It's a negative effect. And likewise, for agriculture versus services, again, the logit normal model says there's no effect, beta model says there is one on dispersion. Okay, so we've got disagreement, and that raises the question of which model is the better model. Okay, well, to compare these models, we can look at their AICs. And so this table shows the AICs for each of these models in each of the probability ratios, the 5 probability ratios that we have. And we can see that for hypothesis 1, the beta regression model is doing better than the logit normal model is. Its AICs are consistently lower. Whereas for the logit normal model, the opposite is true. For the second hypothesis, the logit normal model is doing better than the beta model is. It'd be really great then if we could somehow have a hybrid model where we used the beta regression models for the first 3 probability ratios and the logit normal model for the last 2. And notice we can't do that in ordinary normal theory regression because we have to use multivariate normal distributions. It assumes a normal distribution for all the marginal distributions. However, the model for doing this for actually being able to do this hybrid model is called a copula. So I'm going to give you a very brief hand-waving introduction to copulas. Copula model requires the following steps. First, we convert the data to ranks and divide by the sample size, which gives the marginal quantiles. The quantiles are the marginal distributions. This strips away the influences from the marginal distributions because the quantiles have a uniform distribution. So the associations between the quantiles are a dependency structure that is not being contaminated by influences from the marginal distributions. Ordinary correlations are not like that. They're a product of both this dependency structure and influences from the marginal distributions. So a copula is a model of the associations between between pairs of these quantiles. And copula models use functions of their respective cumulative distribution functions, or CDFs, to do this. So in order to get this done, we have to choose a joint CDF model that we want to use. What I've chosen is a multivariate D distribution, where the degrees of freedom is a parameter that can be estimated in our copula model. So the joint CDF model uses the marginal quantiles to determine its own marginal CDFs, and from that, estimates the correlations between the pairs of quantiles. So there we go. It's not bad. In the left-hand table, the red numbers are the estimates from the quantile, from the copula model rather, and the black ones are the real deal. They're the empirical correlations between the quantiles. And the right-hand table shows absolute differences between them. The biggest difference is about 0.1. Smallest differences are around 0.002, 0.005. So we're not doing badly. Okay, so what conclusions can we get from all of this, from this trip we've taken through compositional data analysis? Well, first of all, compositional data, or ipsative data, are not pathological at all. We can analyze them with just plain old ordinary linear regression if we want, by converting them to log ratios. Simple. However, not all the problems for analyzing these data have been solved, and in particular, the zeros and ones problem could still be a hassle. It's something that's where we still don't quite have a completely satisfactory way of doing things. We've got ways of getting around the problem, but they're not, we haven't got a unified approach yet. Compositional data also can be analyzed by converting them to probability ratios instead of log ratios. And that expands the toolbox because now we can use things like beta regression and other kinds of distributions that are suitable for modeling variables that sit between 0 and 1. However, it's arguable that this expansion introduces some more problems as well. For one thing, how do we choose among models or distributions? Also, not all of them are easy to interpret. So there's still some things to work out there. Nevertheless, I think I've shown that looking at data from a compositional point of view can produce novel insights. Recall the emergency department example, where turning the time spent in the emergency departments into a compositional structure enabled us to answer questions that just could not be analyzed or answered other ways. And there are a lot of data out there in psychology that could be converted into compositions. I think even a skeptic probably can agree with that assessment. Okay, so I think, if I'm not mistaken, this is the end. Thanks.
Okay, I'll stop the share there. Thanks very much, Mike. I'll hand over to you. Do you have any extra comments you want to make before we go to the floor for questions?
No, except that I'll be grateful for any feedback on the extent to which any of this made sense, because Steve Brunel and I are trying to write a sort of a tutorial paper on this stuff.
Great. So I can see Michael Plato with his hand up. So I'm just going to allow you to talk, Michael. Hopefully you can speak now.
Okay, hi, can you hear me? Okay, so thanks, Mike. I got some of that. My skills usually extend really no further than ANOVAs, right? So if ever there's a nuclear holocaust, the most I can do to contribute to society is run a 2x2. So I didn't fully get that, but here's my question. You started off and you made reference to the possibility or the fact that these ipsative measurement is, at least under certain circumstances, better than a standard Likert scale. And you showed us some data where you tried to make that argument, but I'm struggling to see how I might use it in my own research. Because you chose very specific kinds of examples that were, time in emergency. But I don't ask that. I say, how much do you like this? And so is your suggestion, is it that kind of box suggestion? If you had 100 points, how many would you put into, how much do you like it? And how many would you put into some other dimension and split between them? And if that's the case, what's the difference between that and simply asking people to rank order? So that's my
Okay, good question. And yeah, this seminar was light on in terms of examples from psychology about how these kinds of measures could be constructed and how they could be applied. there's actually a pretty good review paper that came out in 2015, which the reference I can send to you,
Yeah.
which delves into that a lot more than I have. But briefly, yeah, if you get people to rank order things, then then you're doing a kind of ipsative measurement process there, because the ranks are constrained. Likewise, if you say, here's 100 points, how would you divvy them up across these different things? Then you're also creating compositional data that way. But I'll send you the reference to the 2015 paper, because that goes a lot more. That goes into the history of ipsative measurement in psychology.
And then if I can just follow that up. So, I mean, one of my favorite papers, knowingly and intentionally violates assumptions of analysis variance by doing an ANOVA on ranks. So this is a paper by Dave Messick back in the 1980s in Judgments of Fairness. Basically, what he effectively did within subjects was to have an n by n matrix, if you will, of that was populated for each subject by the ranking of these total n stimuli. It was not quite that way, but basically that way. And then so everybody has this within subjects, let's say 2 by 2, a set of rankings. It was a little more than that. And then he just analyzed that matrix with an ANOVA, within subjects ANOVA, and had great data as far as I could tell. So why shouldn't I just do that? You're muted, Mike.
There are a couple of reasons. One is that you've only got ranks, so straight away anything like an assumption of normality goes out the window. You've got data that essentially have a flat distribution, because that's what ranks are.
Yes.
And so there are a couple of alternatives, in fact, that you could use. One would be non-parametrics. That would be one way to go. But another way would be this compositional data analysis method, which actually would have more statistical power than non-parametrics would, and in a sense would also enable you to kind of have your cake and eat it too, by taking the ranks, dividing by n, and therefore converting them into proportions. You could then take the logs of those, logs of ratios of those, and convert them into data that actually can be legitimately analyzed.
Yeah, that makes sense. I got that one. Yeah, that's good. Yeah.
So you could do that.
So I will let people ask other questions, but if there are no other questions, I'll put my hand up again for another one. So.
Okay, I can see Diana. I'm just going to click there you go. You should be able to talk now.
Hi, Mike. It's not Diana. It's Xuan being adopted by Diana. Because, yeah,
I'm still here.
I mean, I'm very grateful that she adopted me, because I can't use my there are people working in my office. I don't want to disturb them. And Mike, I can follow some of your talk. Thank you. And I think that there might be a typo when you're talking about the additive log ratio. So you have this, you take the logistic of y1 over y3. And then in the second column, the last column probably should be the logistic of y2 over y3 instead of keep on it, so y1. Apart from that, is that you got quite a few parts that I couldn't follow. I'm so sorry. When you're talking about the log, the central log ratio, there is something like a D. I didn't quite get what that D is. If you could kind of like elaborate a little bit. And I didn't quite get what the hurdle model is either. And then, yeah, but what I can get I mean, to end on a positive note, you know, I'm thinking about this. It's actually very interesting if you're thinking about assessing kids with dyslexia and then providing them with different interventions, and you'll have kids that when you're assessing them, then providing them with phonological awareness treatment, giving them a while, and then giving them the vocabulary treatment, give that for a while, and then see whether their improvement actually could get better in different ratings, whether their skills could improve a little bit better, because the time that you split on different child in their dyslexia treatment is add up to 1. So seems to be compositional data that's in that sense. Really, Mike, if you want to give this as tutorial, you totally lost me on the hurdle model, and for copular, I mean, even that I have heard you talk about it in your office informally, I don't understand what CDF is. So do you mind elaborate just a little bit more, please?
Okay, well, obviously there's a fair amount of material in the seminar that I just gave, which gets unpacked a lot more in the paper that Steve Brumell is writing. So hopefully there's some of that stuff at least gets explained more there. In some respects, you can kind of put the copula stuff aside for this. The focus really is on analyzing the compositional data. The copula stuff is really just there to handle the dependencies between the different parts of the composition. So it's kind of a sideshow. So really the main thing to get out of all of this is the fact that if you've got a dependent variable that sums across a bunch of categories to a constant, like hours of the day having to add up to 24, for instance, when you're looking at different activities during the day, then you can analyze those data by taking them as proportions and then taking ratios of them, ratios of those proportions. So for example, taking the amount of time spent at work relative to the amount of time spent sleeping, and take the log of that ratio. Once you do that, then you can just analyze it with ordinary ANOVA, linear regression, that kind of thing. So really the main point of the talk is that with these compositional data, you can convert them into a non-compositional form that enables you to use conventional methods of data analysis on them. That's really the main take home.
Sorry, I think I put you back on mute there. Thanks, Mike. I can see we've got another question from Bruce. So Bruce, I'll just unmute you there.
Thanks, Erin. Thanks, Mike, very much for those insights and the tools. I think it's really exciting given the measurement advantages of Ipsative data. So thank you very much for sharing that. Another kind of Ipsative measurement that's gained some popularity in certain sectors is data from things like discrete choice conjoint experiments. And on the surface of it, and it might be just to my limited understanding, the ways in which they analyze that data seem to depart from the ways that you're suggesting here. I mean, most often I've seen those analyzed with hierarchical Bayesian models. And I'm just wondering if you could comment on whether those are substantive differences and what those might be or what we should be aware of, or do they devolve into some sort of common kind of underlying mathematical mechanism?
My understanding is that those conjoint measurement data usually are discrete, right? So people are being asked to choose one out of several alternatives under a wide variety of circumstances. And And so those data can be analyzed with, as you say, a Bayesian hierarchical model, but at the heart of it will be some kind of binomial model or a logistic regression model. These data that I've been talking about are generally treated as if they're continuous on some kind of scale, and so that's why the focus at the beginning of my talk was on how to convert these into something that can be analyzed with with linear regression. I didn't mention anything about using Bayes because I thought that would complicate things even more than they already are with this kind of topic. But yes, you could analyze compositional data using hierarchical Bayesian approaches, no problem. So the difference, I suspect, between the kind of data that you're talking about and the sorts of things I was talking about really just comes down to whether the dependent variable is a discrete thing or whether it's some kind of scale.
Okay, that's great. Thanks for that clarification. I really appreciate it.
Thanks, Bruce. Mike, can you see that question in the chat from Nicole?
Let's see.
About changing zeros to be a small positive value.
Yeah, okay.
You can see that one? Yep.
Yep. Yeah, that was actually something that I did mention in the talk, but it may have kind of floated by. There was a slide where I talked about adding a small positive constant, which I called epsilon, to 0, and therefore also subtracting it from 1. And Nicole, you're quite right. Epsilon could be 0.0001 if we want. So we'd be converting the zeros into 0.0001, converting the ones into 0.9999, and that can work fine. The main limitation to it is that if we have lots of zeros and lots of ones, then probably what's going on is that the zeros and ones are somehow qualitatively different from the values that are neither 0 nor 1 in the composition. Now I'll give kind of an analogous sort of example. Let's suppose we're going out to do a survey on smoking behavior, and one of our questions is, how many cigarettes do you smoke? Did you smoke last week? Okay. We're going to get a lot of people, if we do this, for example, in most parts of Australia, we're going to get a lot of people who don't smoke. So they're going to tell us 0. They're telling us 0, not because they're a smoker and they just didn't happen to smoke any cigarettes that week, but it's because they're not smokers. So if we think about what's going to predict who's a smoker and who's not a smoker, those variables probably are going to be different from the variables that will predict how many cigarettes a smoker smoked in the last week. And therefore, we really want to have two models, two separate models. One for the zeros versus everybody else, in other words, the non-smokers versus everybody else, and another for the smokers and how much they smoke. And that's why I introduced the idea of a hurdle model. A hurdle model actually is a pretty old idea. It goes back to the early 1970s at the very least. But the basic idea behind it is what I've been talking about, namely that if you've got a lot of zeros in compositional data, and it's not due to sparsity in the data, then it may be the case that people who are giving you 0 are a separate group. They're qualitatively different from the people who are not giving zeros. So if there aren't a lot of zeros and ones, then adding a little constant to the 0 and subtracting it from ones will work perfectly fine. That's what a lot of people do. But if there are a lot of zeros and ones, then probably it's worth thinking about whether that's the best strategy to have.
Thanks, Mike. And there's a thanks there from Nicole. Hurdle model makes sense. Michael, we've got time for one more question. I'm gonna There you go.
There are none from anyone else. So thanks, Mike. I just going back to one of the first slides. So where you were describing calculating these values into proportions. I guess this just exposes my naivety in the process. But if I've got 3 values, which is what you had, and I take value 1 and I divide it by value 3, and I would take value 2 and I divide it by value 3. That's the example you gave. In my mind, maybe this is wrong, but my 2 new values are not simply not independent because they all sum to 1, but they're not independent because they also have value 3 as part of them. So aren't you reintroducing a kind of dependency or relationship by having the same, like, so why don't you just use value 1 and 2 rather than 1 and 2 each divided by the same value 3?
Okay, well, that's not a naive question, and actually that's what people frequently used to do. They would say, I'll just ignore value 3 and I'll just analyze values 1 and 2. One of the difficulties with that is that values 1 and 2 may also be linked with each other. It may turn out, for example, in my particular example, that that there was a trade-off happening between the amount of time that people spent in registration and the amount of time that they got to spend being assessed by nurses and physicians before they went on to treatment. So you don't necessarily get off the hook by just looking at part of the composition and leaving out one of the things, so you get rid of the sum constraint. One other problem is that by not taking value 3 into account at all, you're missing part of the picture. You're missing whatever is going on with value 3. And then to get back to the first point you raised, yes, you're right. If I take y1 divided by y3 and y2 divided by y3, then it's pretty likely that those are going to end up with being related in some way. But the nice thing about taking logs of them and ending up with things that are now on the real line is you can say, okay, I'll use a multi-level regression model, right? I've got 2 of these things down at the subject level. I've got 2 of these things. I'll just take into account the correlation between them.
Okay, yeah, got it.
A mixed model, and so bingo, you're in conventional analysis land. You're just using a mixed model.
Yeah, okay, got it. Yeah, good. Thanks for that. Yeah.
Beautifully timed. Thank you very much, Michael, and other attendees for some great questions. Thank you, Mike, for a really interesting presentation. And we'll make sure this is available to people to go back and have another look, let it soak in a little bit. And then I'm sure Mike is up for having some extra feedback as well, given that this is an ongoing project, Mike. So thank you very much, everyone. And we'll see you next week, same time.